How do large capacitor banks generate pulsed power? Imagine a quick burst of energy so powerful it can light up a laser or launch a projectile at incredible speeds. That's what large capacitor banks do. They store energy and releases it in a flash. First, think of a capacitor as a tiny energy reservoir. When you connect it to a high-voltage power supply, it charges up, creating an electric field between its plates. The more capacitors you connect in series or parallel, the more energy you can store. The energy stored depends on the capacitance and the voltage squared, which means doubling the voltage quadruples the stored energy. Next, the charging process is slow and controlled. The capacitors fill up with energy over seconds or minutes without sending a big current to the load. This way, they safely store a lot of energy without causing damage. When it's time to generate a pulse, a trigger activates fast switches. These could be spark gaps, vacuum switches, or semiconductor devices. These switches are designed to open and close very quickly, almost instantly connecting the capacitor bank to the load. Once the switch closes, the stored energy discharges rapidly. The current shoots up in a matter of microseconds or even nanoseconds, creating a high-voltage, high-current pulse. This pulse is much stronger than the steady power from the original supply, but it lasts for only a very short time. Designing the circuit carefully is key. Engineers minimize inductance in the discharge path because inductance opposes sudden changes in current. Low inductance allows the current to rise sharply, producing a clean, powerful pulse. Sometimes, pulse-shaping devices like pulse-forming networks or lines are used. These combine capacitors and inductors to control the shape, duration, and strength of the pulse. This helps tailor the energy releases for specific uses. Large capacitor banks are used in many high-power applications. For example, pulsed lasers need intense bursts of energy to generate beams. Railguns use them to accelerate projectiles at high speeds. Fusion research relies on these banks to deliver quick, powerful energy bursts to plasma or laser systems. In essence, these banks work by storing energy slowly and then releasing it all at once through rapid switching. The challenge is to manage the energy, keep the circuit low in inductance, and shape the pulse to suit the task. That's how they produce the pulsed power that drives some of the most advanced technologies today.